Some homework from Monday, guys, page 533 and 534. We'll take a look at 533 first of all. Pretty sure we need to go over question number 2, correct? And we can do number 1 as well if we need to, yeah. So number 1 and 2. 1 says a metal sphere with a charge of negative 2.5 times 10 to the negative 9. Probably a good idea to circle that to remind us that it's a negative value. It's 1.5 centimeters. Probably a good idea to circle that as well. To the left of a metal sphere that is a charge of 1.5 times 10 to the negative 9. A third one that's also negative is 2 centimeters to the right of the second charged sphere. They form a line. What's the net electrostatic force on sphere 2? So let's draw it out here. We'll call this sphere 1, and it's a charge of negative 2.50 times 10 to the negative 9 coulombs. There's a second one that has a charge of positive 1.50 times 10 to the negative 9 coulombs. And there's a third one that has a charge, again, we remember to put it as a negative because we circled that. It's negative 1.00 times 10 to the negative 9 coulombs. Now we got some distances in here as well. It doesn't really matter whether we label them in meters or in centimeters. We just got to remember when we do our calculation to convert them to centimeters. It might make sense now just to do the conversion. Then we don't have to worry about forgetting later on. 0.015, I remember you divide by 100. Okay, I don't know if anybody said 0.15. But if you did, that's not an uncommon mistake. It's wrong, but it's not uncommon. 0.015 meters, and then of course over here we have 0.020 meters. We want to find the net force on which one? The net force on the second sphere, the middle one. We could do it on any of them, but we're trying to find the force on the middle one, and usually that's what we end up doing, usually. All right, so we're doing this. We first have to pretend that sphere 3 isn't there. So all we have is sphere 1 and sphere 2. Both of these are oppositely charged. One's positive, one's negative. If we have two charges that are opposite, positive and negative, then what do we know about those two charges? Do they attract or repel? They're going to what? Sorry? They're going to attract. Good. They have to attract because they're opposite charges. Now that means that charge number 1 is going to be pulled towards charge number 2. But we don't really care, because we're not trying to find the force on charge number 1. Rather, we're trying to find the force on charge number 2, which, because of number 1, is pulled to the left, pulled towards number 1. We'll label that F12, the force of 1 on 2. Now, let's pretend 1 isn't there. 2 and 3 are opposite charges as well. They're going to attract or repel. By that first law of electricity, they're going to attract each other. That means 3 will be pulled towards number 2, but we don't really care because we're not trying to find the force on 3. 2 will be pulled towards number 3. We'll call that F32, the force of 3 on 2. So we've got a free body diagram drawn, which is important because we need to find those forces and then add them up. And when we add them up, we have to know what direction to put them in, positive or negative. And we're not going to make them positive or negative based on the sign of the charge. Look, they're both negative right here. Okay, we're going to make it positive or negative based on the direction. So we're going to look back to that free body diagram and determine then whether it should be positive or negative. All right, so let's say we got to find both of those forces. F12 is going to be equal to K Q1 Q2 over R squared. Looks like that law of gravitation, right? Looks a lot like that law of gravitation. But difference is, of course, Coulomb's law can be attractive or repulsive. It involves charges instead of masses. And is it a smaller or a bigger force than gravity? Is the electrostatic force smaller or bigger than gravity? Bigger. It's bigger. It's way bigger than gravity. We know that because of that constant. K is 8.99 times 10 to the 9 instead of 6.67 times 10 to the minus 11. Notice the units here. It's still coulombs, but it's 10 to the minus 9 coulombs or nanocoulombs. That'll often be abbreviated as an NC, 2.5 NC, as opposed to written 2.5 times 10 to the minus 9. Notice when we're solving this, we avoid using the third charge completely. Okay, it's irrelevant for this force of 1 on 2. Does anybody have a value for that force calculated already? Okay. 1.4983 times 10 to the minus 4. Okay, thank you. Now let's do the same thing with the force of 3 on 2. It's KQ2 Q3 over R squared, or the constant. What do we get for the value of Q2? It was 1.5 and 1.0. That was a negative 1.0 times 10 to the minus 9, but remember what we said? We're dropping the sign of the charge whenever we plug it into an equation. For us, the sign of the charge is only going to be used to determine whether it's attractive or repulsive, not in determining whether it's right or left. Okay, we're going to use, for us, the negative will mean direction, okay, not the sign of the charge, at least in the equation. That is, it'll mean direction. The distance that we have that separates them is going to be 0.020 meters. And we got to square that, of course. What do we get when we do the math on that one? 10 to the negative 5, thank you. If we have F12 and we have F32, and F12 is to the left, not because this is a negative charge right here, but because the force is acting to the left, then we're going to make it a negative value. F32 is acting to the right, so we're going to make it a positive value. When we add those up, the first one being a negative, the second one being a positive, we should get negative 1.16 times 10 to the negative 4 newtons. That negative means that the net force, the total force, the unbalanced force on this is acting to the left. Yep. If charge 3 was positive, did you say? Okay. No, if charge 3 was positive, well, the force of 1 on 2 would still be to the left, right? But if charge 3 was positive, then it would push charge 2 to the left as well, and the force of 3 on 2 would be to the left. So then we make them both negative. Or you could, in this case, it might be easier just to make them both positive in that case, right? But you have to make them both the same direction if charge 3 is positive, right? The whole reason we draw this free body diagram is to see what the direction of the force is. But we can't just say, automatically that it's a certain direction. We have to look at each of the charges to determine which way is it going to be pushed or pulled as a result of the other charge. Okay, 3 here would be pulled to the left. But that's not what we're trying to find the force on. We're trying to find the force on 2. It's pulled to the right. But if 3 was positive, it would go the other way. So it would look like this. Yep. No, that's a good question as well, though. If we were trying to find the force on number 1 as opposed to number 2. Can I erase that, by the way? Does everybody still need that? Okay. If we're trying to find the force on number 1, we won't solve this, but we can show you exactly what you do here. Trying to find the force on number 1, there's still 2 forces acting on it. There's the force of 2 on 1 and the force of 3 on 1. Okay, 2 pulls on 1 and 3 pulls on 1 as well. 1 and 2 are oppositely charged. That would mean 1 would be pulled to the right. This time we're going to call this, instead of F12, we're going to call it F21, the force of 2 on 1. But there would also be a force of 3 on 1. It's negative, I guess. So it's going to push it away. Force of 3 on 1 is pushed away to the left. Does that make sense? All right, so now we'd still add those up. We'd add up F31 as a negative value and F21 as a positive value. Be careful, though. Here's a mistake that people make go up. You're calculating the value of F31. And it's K Q1 Q3 over R squared. What's R? Those two added together, right? 0.035 meters squared. Now, what is probably the single biggest mistake that people make with this question? And by the way, a question like this appears on your diploma exam almost every time. Almost every time. There will be a number of you that mess up on this question, even though it's not a particularly difficult question. Okay, where do people mess up? The single biggest mistake you can probably predict. If you just, no, although people do make that mistake, and that will almost certainly be an option for you if it's multiple choice, if you forget to square the R. But that's not the single biggest mistake that people make on this. Yep. Not so much forgetting to drop the positive and negative and plugging it into the equation, but that can lead to the mistake that people make, although it's not the only way to make that mistake. In the end, people get these directions wrong, especially if you have them in opposite directions. What do people do? They make them both positive. They add them up. And when they make these both positive, what happens? They find an answer. It's multiple choice. It's option B. Let me pick that one. But it's wrong. All right? So be very, very conscious of that. Be very, very careful that you don't mess up on that direction. Like, think about it. This is one question. But this is one question that will almost certainly appear on your exam. And it will be worth 2% of your exam, which will be worth 1% of your overall Physics 30 mark. Okay, 1% of Physics 30 is this question that we just did. I think we can handle that. But don't mess up on it. Okay, if you're going to mess up on something that's a lot harder than this question. Okay? And if you're having trouble with this a little bit right now, that's okay. But make sure you come and see me so that you don't have trouble on these questions that are manageable questions. Again, if we mess up on something, we want it to be a lot harder question than that one. If we mess up on something, we want it to be like question number 2, for instance. It's a lot harder. I don't think, to be honest, you'd see a question like number 2 on the exam because I think it's too hard to put on the exam, too hard mathematically. But we're going to go through it anyways here just in case. And because, you know what, whoops, because it's a good exercise to go through, let's just try this. There we go, that's better. It's a good exercise to go through, even if it's not a question that's going to appear on a unit test or an exam or whatever. 2 says, in the situation described above, the first and third sphere remain at their original positions. So we're going to put 1 and 3 here. We're going to draw those first. We know that they're 3.5 centimeters apart, or 0.035 meters apart. The second sphere is going to be somewhere in here. We don't know where, so we can't draw it in the exact right position, but that's okay. We need to know where the second sphere is going to be so that the net electrostatic force on it would be 0. What are the values of the charges? Charge 1 was negative 2.5 times 10 to the minus 9. 2 was 1.5 times 10 to the minus 9. And 3 was negative 1.00 times 10 to the minus 9 coulombs. All right. We need to know this value right here. We need to know where charge 2 has got to be in order to have a net force of 0. Now, your sub yesterday, some of you said that your sub went through this with you, or at least with some of you yesterday, and you were wondering if there's an easier way to solve it. I'm curious if he did it exactly the same way as me. If it looked complicated yesterday, he's probably doing it the same way as me, because in the end, this is a tricky question mathematically. What we have to recognize here first is that the force acting on number 1 is, on number 2 is due to charge 1 and 3. Let's draw that free body diagram first of all. 2 is pulled towards number 1. We're going to call that F12, the force of 1 on 2. 2 is pulled towards number 3. We're going to call that F32, the force of 3 on 2. Now, if the net force is 0, what do we know about the values of those two forces? They've got to be equal. Right? You can't have a balanced force if one force is bigger than the other. They've got to be equal to each other. So let's set them equal to each other. If we know they're equal, then let's make them equal. F12 is equal to F32. Now, this is not a huge deal, but technically we should put it to be correct. we should put the absolute value signs around it. Because in the end, those two forces aren't equal, right? One's to the left and one's to the right. But the magnitudes are equal. Now, if you don't put that absolute value sign, you're probably still going to get the question right, as long as you do everything else right. But we'll try to write it correctly here anyways. All right, F12 is K Q1 Q2 over R squared. Would you agree with that? That's what we did before in the last question. K Q1 Q2 over R squared. The value of F32 is K times Q2 Q3 over, well, we can't call it R. It's the distance that separates 2 and 3, but it's not the same distance that separates 1 and 2. And that we called R, so we can't call this one R. We call it X or D or whatever we want, really. Tell you what I'm going to call it, though. I'm going to call it 0.035 minus R. Because if you think about it, this distance right here has to be 0.035 minus R if this is 0.035 and this is R. Does that make sense? Okay, is that what he did yesterday? Let's cancel those K's because it appears in both terms, right? Let's cancel the Q2's because it appears in both terms. That simplifies it a little bit, saves us from putting some other numbers and exponents in there. We're left here with Q1 over R squared equals Q3 over 0.035 minus R squared. So far, so good? It's not crazy so far, is it? I mean, it's even thus far, it's a challenge question for sure. Physics-wise, though, the hard part's over. Math-wise, we still have a little ways to go. Yeah, math-wise. All right, let's try to simplify this a little bit. Let's take the R squared up by multiplying, the 0.035 minus R squared up by multiplying. How's that? Is that okay? Oh, here's the thing, guys. We got to solve for R here, right? Does anybody have any idea how to solve for R here? It's actually not as bad as you might think. Okay? I'll tell you what my instinct is when I see this. I'm not sure why, because it's not the simplest way to do it. My instinct when I see this is to FOIL that. 0.035 minus R, right? You got to FOIL that, right? Anybody think that? That's a perfectly valid thing to do. But it gets kind of ugly mathematically. There's an easier way. Let's first of all get this by itself. Say 0.035 minus R squared equals Q3 over Q1. What do you got times R squared? Good. Now what? Square roots both sides. Let's square root both sides. So we've got 0.035 minus R equals the square root of Q3 over Q1 times R. Does that make sense? I've square rooted Q3 over Q1. I also square rooted R squared, but square root of R squared is just R. Let's get a number for that, okay? Let's get a number for that square root of Q3 over Q1. The charge of Q3, I believe, was 2. Was it 2 times, no, 1 times 10 to the minus 9? 1 times 10 to the minus 9. And Q1 was 2.5 times 10 to the minus 9. Now, The 10 to the minus 9 actually cancels. So all we have to do here is say 1 over 2.5, take the square root of that. That's going to be 0.04. Square root of 0.04 would be 0.2. Is it 0.2? So 0.035 minus r equals 0.2 r. Is this what he did? Okay. Okay. All right, so now it's not so bad. Let's take this minus r over to the other side by adding 0.035 equals, well, what's 0.2r plus 1r? 1.2r, right? If you have 0.2 of an apple and you add an apple to it, you have 1.2 apples. If you have 0.2 of an r and you take an r over by adding, then you have 1.2r. So r becomes equal to 0.035 over 1.2, which is what? 0.029? Okay. 0.029 meters. What is it? Oh. So this number wasn't 0.2? Oh, you guys told me it was right. Somebody told me that was right. Okay, what is that then? What is the square root of 1 over 2.5? Okay, so now let's take the r over by adding again. 0.035 equals 1.6325 r. R becomes equal to 0.035 over 1.6325. What does that equal? .0214 meters. Let's see what we have for an answer here. It says 2.14 times 10 to the minus 2, right? 0.0214 meters. I'm not even going to ask you how many people would have got that right if it was a test question, because the answer is probably 0 of you, and that's okay, because that's a real challenge question. But does it make sense to you now? You know, I'm not even asking you, could you do this again if you saw this, you know, a month from now on a unit test? Okay, I'm not asking you that. I'm asking you right now, as we've gone through it, does it make sense? That's the important thing. Because quite frankly, I don't think you're going to have to do that on a unit test. Well, I can tell you for sure you won't have to do that on a unit test because I make that up. I don't think you'll have to do that on a diploma exam either. I think if you understand it, then that's good because your mind has grown a little bit from the process of understanding it. Whether you can actually do it by yourself isn't really all that important if we're not going to see something like that. Okay? We just want our mind to grow a little bit so other questions seem a little bit easier. Okay? Is that good? All right. I know how much you guys are looking forward to seeing that question done. Now it's done. Now we get to look forward. Now we get to look forward to seeing page 534. The other bit of homework from Monday. And this one we had. This is a two-dimensional one, right? Let's do one of these questions. Which one do you want to do here? Which one? First one? Okay. Second one might be a little bit easier because you have the diagram already drawn for you. You don't have to interpret the wording of it. Okay, number 1 says a small metal sphere, sphere X, with a negative charge of 2.5 is directed to the left of another one, sphere Y. That's negative, by the way, and that's centimeters. And we got positive charges for the rest of them. Yep. All right, so this is going to be X. This is going to be negative 2.5 coulombs. And it's to the left of sphere Y, which has a charge of 3 coulombs. But it's, 1.2 centimeters, or 0.0120 meters. Doesn't really matter how I label it. Just remember that if I label it in centimeters, I've got to convert that. Sphere Z. Oh, this one's a good one. Let's see here. What is it? 4? Yeah, 4 times 10 to the, just 4, I guess. 4 coulombs. And the distance is the same. Okay, we want to find the net force on Y. All right. Let's take a look at the force of X on Y. X and Y are oppositely charged. What does that mean about attraction and repulsion? They're going to what? Y is attracted to X. X is also attracted to Y, but we don't really care about that, right? Y is attracted to X. We're going to call that Fxy. Now, you can name it whatever you want. I'm naming it Fxy so that we can try to keep straight which force we're dealing with here. In the end, if you want to call it Fq, okay, go ahead. In the end, it is the force between X and Y, force of X on Y. Now, Fzy, the force of Z acting on Y, it's going to be upwards because Z pushes Y away. It's a repulsive force. Z is going to be pushed away downwards, but we don't really care what happens to Z because the question is what happens to Y. So we've got our free body diagram drawn with our two forces. Now we have to calculate each of those forces. Fxy is going to be kqxqy over r squared. Notice we're dropping the sign of the charge there. Anybody have a value for that? For Fxy? 14. 4.68 times 10 to the 14 newtons. That's a big force. Can anybody suggest to me why that's such a big force? What do we usually deal with when we're dealing with these questions? What are the charges usually like? Well, microcoulombs or even nanocoulombs, right? This is coulombs. So these forces are going to be big because the charge is massive, right? We're dealing with coulombs here. Okay, let's calculate Fzy now. Does anybody have a value for that one? We know how to plug in our numbers into that, right? It's just 7.49 times 10 to the 14. Okay, what are we going to do with this now? We say Fxy is negative, Xzy is positive. We just add them up. Well, we do add them up, but we have to add them up according to the laws of vector addition. The rules, I should say, of vector addition, which says that Fxy is to the left, Fzy is up, and the resultant vector, the force that we're trying to find here, is the hypotenuse. We can find F by doing the Pythagorean theorem, and when we do that, I think we should get 8.83 times 10 to the 14. And we can find theta by using the inverse tan function. And when we do that, we should get 58 degrees. Okay. And the notation that they use here, the 122, you guys know what that means? This is 0. This is 90. This is 180. So 122 would be 58 degrees away from 180. Don't worry, don't panic about that notation, okay? We don't use that notation on unit tests and on exams, and that's why I haven't really taught it to you, the whole 120, the whole 122 thing. I'm going to ask you to do question 42 right now, and then we're going to submit that as numeric response question number 1. Let's take a look at it here now. Two conducting spheres of identical surface areas. Sphere A has a charge of 4.50 microcoulombs. Sphere B has a charge of negative 2.40 microcoulombs. They are brought into momentary contact and separated to a distance of 2.5 centimeters. When they're brought into contact, right away, okay, we don't know what the question is going to ask us, but when they're brought into contact, we know that they're going to balance charges. So we know we're going to have to add those up and divide by 2. Let's do that right now, even before we know what we're asked in question 42. 4.50 microcoulombs plus negative 2.40 microcoulombs. We divide that by 2. That's going to give me, what is that, 2.1 divided by 2? 1.05. Is that right? So the charge of both of them now becomes 1.05 times 10 to the minus 6 coulombs. Now we want to find the force that acts between them. It's going to be K Q1 Q2 over R squared, or 8.99 times 10 to the 9 times 1.05 times 10 to the minus 6 times 1.05 times 10 to the minus 6. And we divide that by 2.50, right? Is that right? No, what's wrong with that? It's in centimeters. We got to convert it to meters. We're not going to forget that because we circled it. 0.0250 meters. We square that. And I think when we do that, I think we get 15.9. Is that right? Now, I know this is what some of you did. Some of you used a charge of 4.5 and 2.4. Okay, if you do that, then you get the force that exists between the two before they're touched. That's not what we're looking for. Okay, some of you, when you found, you had the right idea here, but some of you didn't put a negative in for the 2.4. Some of you just went 4.5 plus 2.4 divided by 2, and then you got a charge on each one of them of, it would be somewhere in the range of 3.5 or something like that, microcoulombs. Well, that's wrong, because we got to account for the negative in there. And then I know at least one of you said 1.59. So what you did there is said, oh, okay, I got to put it in scientific notation and put the base in. Or does it say put it in scientific notation? Sometimes it does. Sometimes it'll say b times 10 to the w. We want the value of b. Okay, if that's the case, then we'd say 1.59. But if it just says what's the answer, then we'll leave it in the notation that it's in, standard notation, which is 15.9 newtons. Okay, good. I'm going to assign a few questions for you to work on for homework here tonight, okay? I'd like you to do the following questions on page 538, please. All following questions on page 538, please. Questions 1, 3, 5, 7, 9, 1, 3, 5, 7, 9. In other words, all the odds. Okay, all the odds. And 2, 4, 6, 8, 10. All the evens as well, please. Okay. I don't care what order you do them in. If you want to change the order of those a little bit, that's okay. But I'd like you to do all the odds and all the evens, please. Up to number 10. Got it? We had a couple bits of homework for last night, 548. You guys are okay with that? We also had worksheet number 6, questions 5 to 8. And we also had worksheet number 7, questions 1 to 2. You guys want some answers for those? Okay, worksheet number 6 for question number 5. We got a force of 8.22 times 10 to the 28 newtons. And we got an acceleration of 9.03 times 10 to the 58 meters per second squared. That's a big acceleration, right? The fastest, sorry? Would it move to the speed of light? That's a good question. The fastest anything can go is the speed of light, 3 times 10 to the 8 meters per second. Okay, this is a number that's way, way bigger than that. If you get a speed anytime it's bigger than 3 times 10 to the 8, you're wrong, because it can't be bigger than that. But you can get an acceleration, whatever. There's no upper limit to acceleration. All this means is that this charge, this electron, would accelerate from rest to a number that was approaching the speed of light incredibly quickly, unbelievably quickly. Would it actually reach the speed of light? No, it would not. But would it approach the speed of light, get to a number that was close to the speed of light? Yes, it would, and it would do it real quick as well. Number 6, we got an answer here for the acceleration of the alpha particle to be 1.73 times 10 to the 48. Hey, I never told you guys what an alpha particle was, did I? Were you able to answer this question? Where did you get the information for an alpha particle? It's on your data sheet, right? Okay, you don't need to know what an alpha particle is to be able to look on your data sheet and determine what the charge and the mass is. In the end, Dan, you're right. An alpha particle is a helium nucleus, and we'll talk a lot more about that in our last unit. Okay, but right now, it doesn't really matter if you know what it is, as long as you know where to find the information about it. Anyways, there's the acceleration of the alpha particle. Here's the acceleration of the electron. Hey, can you tell me in number 6 why the acceleration of the alpha particle is quite a bit smaller than the acceleration of the electron? Because it weighs more. Not because it's bigger, because it weighs more. It's got a higher mass. The force acting on the electron is the same as the force on an alpha particle. But the force on a heavier object is going to cause a smaller acceleration, right? You push a smart car, you push a semi-truck with the same force. Which one will accelerate at a higher rate? The smart car, obviously, because it's lighter. Okay, question 7 on worksheet number 6. Question 7. We got a force here of 2.88 times 10 to the 13. And question 8, we get a force here of 2.25 times 10 to the 5 newtons. Yes, we can. Yeah. Okay, we're going to take a look at 6 and 8 here. Question number 6. Lorraine asked me about question number 6, and I mean, she knew what she was doing right up until the end there. She calculated the force that exists between the electron and the alpha particle. Okay, that's KQ1, Q2 over R squared. And when she calculated that force using Q1 3.2 times 10 to the minus 19, an alpha particle, 1.6 for the electron, she would have gotten a force of 1.1507 times 10 to the 22 newtons. Now, when she went to calculate acceleration, she recognized that she's got to do A is equal to F over M. When you're calculating the acceleration of the electron, it's this force divided by the mass of the electron, which is on your data sheet. When you're calculating the acceleration of the alpha particle, which that's a symbol for an alpha particle, by the way, not that you need to really know that right now. It's also going to be F over M, and the force is going to be the same. It's an equal and opposite force, right? Newton's third law. But the mass, as we see on our data sheet for an alpha particle, is 6.65 times 10 to the minus 27 kilograms. And because the denominator is a lot bigger, more than 1,000 times bigger, then we're going to find the acceleration is a lot smaller, more than 1,000 times smaller. All right, let's take a look at question number 8 now then. Number 8 says object 1 has an initial charge of 1.00 times 10 to the negative 5 coulombs. We got 3 of them here, right? This is 1.00 times 10 to the minus 5 coulombs. Number 2 is negative 2 times 10 to the negative 5. And charge 3 is negative 3.5 times 10 to the minus 5. We're told that object 1 touches 2 when 1 touches 2, they've got to balance each other out. 1 plus negative 2 gives me negative 1. Divide that by 2, we end up getting 0.5 times 10 to the minus 5. And of course, 0.5 times 10 to the minus 5. Charge 3 stays the same, negative 3.5 times 10 to the minus 5 coulombs. Now it says object 2 touches 3. So 2 and 3 combine here. Object number 1 remains the same, 0.5 times 10 to the minus 5. 0.5 plus negative 3.5 is negative 3. Divide that by 2, we get negative 1.5 times 10 to the minus 5. Now we want to find the force that acts between charge 1 and 3. To find that force, we're going to say K, Q1, K. Q1, Q3 over R squared. That's going to be 8.99 times 10 to the 9 times 0.5 times 10 to the minus 5 times 1.5. Remember, we're dropping the sign of the charge now. Times 10 to the minus 5. And divide that by the distance that separates them, which is 2.00 times 10 to the minus 3. Don't forget to square that. As much as Jesse, when we were asking what's the most common mistake that people make with these questions, and Jesse suggested that it was squaring the distance. Okay, as much as I said, well, no, that's not the most common mistake here. It's still a really common mistake. We do that math, we should get the answer that I gave you, 2.25 times 10 to the 5. Janae, is that okay? Where was the mistake on that? Was it the whole making contact, touching each other, and balancing it? That makes sense now? Okay, good. You're right, Jesse. Both of these should be negative charges, which means that these aren't going to balance it to be negative 1.5 and 1.5, right? They're going to balance it to be negative 0.5 and negative 3.5 is negative 4. Becomes negative 2 times 10 to the minus 5 and negative 2 times 10 to the minus 5. And that makes this last number here 2 times 10 to the minus 5. But we still end up getting 2.25 times 10 to the 5. As I was going through this, I was kind of doing it and just made that little mistake. But when I saw the answer, I just cheated and looked at my answer sheet there. Thank you, Jesse. So, Janae, make sure that you've got that as well. Okay, you're having a little bit of trouble with the whole balancing out thing, and then I go and make a mistake, and I'm showing you how to balance them out. Make sure you pay attention to those negatives here. 1 and negative 2 gives me negative 1. Divide that by 2, becomes negative 0.5. Yep. Yeah, it's the same thing. Yeah. Negative 0.5 times 10 to the minus 5, negative 5 times 10 to the minus 6, exactly the same thing. Yeah, that's okay. All right, finally, you did have a couple questions on worksheet number 7. You know what, I don't think we're going to have time to go over those today. Not even time to give you answers to those today. Did it more or less make sense to you? We'll check them over tomorrow. But did it more or less make sense to you? If not, if you had some trouble, some real trouble with worksheet number 7, please come and see me during scheduled help, okay? Scheduled help today. Good news. No new homework for tomorrow. Have a good night, everyone.